And next up we have Tom Jacobsen, who'll be talking about a new methods for passing substrate over weirs.
My name is Tom Jacobsen from the company called Sedicon, and I've worked a few years with sediments, and it's a great pleasure standing here and using this title for a presentation, because if I were at another conference, we may use another title where sediment is a problem, something we have to get rid of. But again, here, the objective is to pass sediment past weirs and past installations for a positive purpose. So, what I'm going to talk about is a result of a pilot test. That pilot test was made possible thanks to Hydropower Research Center here in Trondheim for environmentally friendly energy, and Eviny, which is a company based in Bergen, one of Norway's larger power utilities. So we had a very good cooperation on this project for the last 4 years. Sedicon, we are a company that does only sediment handling, and we've done so for 20 years and in more than 20 countries. And don't tell our clients, but what we actually do is to turn most of our projects, most of our clients are test facilities for new technology. So we have developed quite a lot of new technology sort of while we are doing commercial projects. So, back to what we have been testing. This is a schematic drawing of a brook intake or of a run-of-river intake. And what happens during floods is that the water with the bed load and the sediments go into the intake or eventually block the intake. And the clean water passes over the spillway, over the weir. But this is a normal situation. This happens a lot of places and all the time during floods. So our idea was to reverse this situation and to install a device that takes out the bed load, the coarse particles, stones and boulders, and pass that part of the flow to the downstream and allow clean water to pass into the intake. That's good for the power plant. That was the objective. But it's also good for the river and to maintain the substrate in the river downstream. So this was the idea. We have tested it. And let's see if I manage to start. Is it next? That's the video. We also did a model test. This is a small scale, but it verifies that a stone up to 700 kilo can be drawn into a device like this. Actually, we did this model test after we did the pilot, but anyway, it works and it demonstrates what we are doing. We also have some knowledge from previously. We have done removal of all kinds of sediments, and this is from an offshore project quite a few years ago. And we have designed equipment for this kind of projects where this is a rock dump that is dredged in an offshore project, and that's done regularly with our technology. So we had some basis before we started this pilot test a few years ago. So, what we proposed to Eviny and to Hydropower was to install a boulder excluder, basically a big pipe, big siphon in a brook intake. It has an external diameter of 1,200 millimeter. Discharges 5 cubic meter per second of water when it works, and supposed to remove stones up to 1 meter in size. What you see here was the concept which we made before we started the project. I'm trying to move it forward, but there it comes. So we got the money, we got the funding, we started the project. We managed to get the equipment to the site. It was a narrow road, but by a few centimeters, we made it. Then a helicopter transport 3 kilometers to the site and the installation at the site. And all went very well here. The transport, the helicopter, and the installation was done in a few days, and was really a good experience. It's not that complex, even though you're away from road and so on. So this is what it looked like in the autumn 2020. It was installed. As you can see, it is big and impressive, and it's situated in beautiful nature in western Norway. And the year after, autumn 2021, we got the first actual confirmation that it's working, because it's supposed to work. It works completely autonomously, but it works only during floods, only when there's excess water. And this is a place without electricity, without any network or data connection. So actually there had to be someone there while there was a flood. And one of the people at Eviny was there, managed to film this, and we had the confirmation that this is working. And that was a great milestone to pass in this project. It is a bit... thanks. Good. The next big test was last November. There was a flood, which is very close to a 100-year flood. At least it was 25% more than a 50-year flood. And a lot of debris, a lot of gravel and stones and boulders would have passed, have entered or did enter into that intake during that flood. That's absolutely certain. We came there in December and found, and that was really a positive observation. Not only that the substrate and the material was removed just in front of the intake, but it was removed from a very wide area, and you can see it's very even and flat, and it's everything down to the very sill of the intake is clean, and that is the largest flood that's been recorded in this catchment since 1983. So we got the comment from Eviny. They were very impressed, and so were we. So it is definitely true. This works. Actually, it works. I'd say it works commercially as well, because we have entered more contracts. We installed one last week at Ullaføre, and here you see it's working, and you can see gravel coming out. We did push as much gravel into the intake of this boulder excluder as we could, and when we started it, we can start it if we like. We started with a vacuum cleaner, suck out the air, and then it starts working. And you can see it's discharging gravel very nicely. And we have also entered into more contracts and with potential contracts and signed contracts for this technology. So the technology is already in the market. And in the context we are here, where the purpose is to maintain substrate in the river, downstream weirs, whatever weir, whatever intake or dam, it is possible. And it's also possible, even though you don't have a normal intake, it can be past a fish barrier or the weirs you have in the river to maintain a water level in the river. So you can maintain the water depth upstream and the sediment transport upstream, and you can refill substrate into the river downstream. And it all happens completely automatically without any intervention at all, and it happens during floods when you have the bedload transport in the river. So it can be done, and with this, I want to say thank you. It's fun working with water, and let me know if you have any questions.
Thank you very much. I think we might have time for one quick question.
I wonder, do you know how much of the gravel that is trapped and how much is restored? And another question, can the same result be reached with having a different kind of spillway in the dam with a lower threshold closer to the river bottom?
Well, the purpose with a dam or with a spillway is to maintain a certain water level, and very often to maintain a volume behind that dam. So having another design which does not, is hard to see. What you can do, of course, is to have gates that you operate, low-level gates, and that's normally done in many intakes. But they need active operation, and in many brook intakes and small hydro and so on, you don't have that. So that is an alternative structure, but it requires a more active operation.
And any ideas of what volumes that were restored? I mean, how much gravel is being transported here with this solution?
As much as comes in. The capacity is unlimited. The one you saw, the biggest one, you could feed it with several thousand tons per hour, and it will still pass through.
Thank you very much.
Thank you. So, coming to the next presenter, it's a pleasure to introduce Markus Noack. Thank you very much. He will talk about the vertical connectivity, also an important issue in our river system, and he's from the University of Karlsruhe. And Markus, please, the floor is yours.
Okay, so can you hear me? Yeah, good, great. So thanks, Christoph, for the nice introducing words. As already mentioned, my talk is about an evaluation concept for vertical connectivity and riverbed clogging in regulated river reaches. So first of all, I want to start with some background information. We already heard a lot about connectivities at this conference. Usually this goes back to the four-dimensional nature of logic ecosystems published by Ward, including the longitudinal, lateral, vertical, and temporal connectivity. And also this is quite an old concept. It is still in use. In 2019, Krill et al. Published in Nature a world map showing the so-called connectivity status index. We also saw this map this morning already. And the connectivity status index includes all 4 dimensions. And we look at the map, we can really see that in the industrial areas, of course, we have limited connectivities, and in the remote areas, we have quite a good connectivity. The paper also goes a little bit deeper. 90% of the limited connectivities are due to river fragmentations, which refers more or less to the longitudinal connectivity. And the other big issue is the flow regulation. This is the temporal connectivity. So in my talk, I want to focus not on the longitudinal connectivity, but on the vertical connectivity, describing the interactions between the river and the groundwater aquifer or the hyperheat interstitial. And usually the vertical connectivity is also connected to the temporal connectivity. I will go on this a little bit later. So when we are talking about the vertical connectivity, we also need to talk about riverbed clogging because it hinders the vertical connectivity. And at least in Germany, the clogging is one reason why we are failing objectives of the Water Framework Directive. So what is clogging? Clogging is basically the infiltration, but also the accumulation of fine sediments in the interstitial of gravel riverbeds, as you can see it on the pictures here. And from an abiotic point of view, this leads to a reduction of the pore volume, the hydraulic conductivity, but also to a reduction of dissolved oxygen. And this is having a biotic impact, especially on macroinvertebrates, but also, for example, on the reproduction of gravel spawning fish. So we developed a multi-parametric approach to assess riverbed clogging. We call it multi-PAC. And one important thing about this approach is that it's a quantitative and a physical-based approach. So we are not working with some qualitative data like class 1, class 2, class 5, and so on. We really want to have physical-based values. And therefore, we are using the particle size distribution based on free scoring. We measure the porosity using a photogrammetric approach. And for the dissolved oxygen content, as well as for the hydraulic conductivities, we are using a novel method with a double packer that allows us to measure vertical profiles of the dissolved oxygen content and the hydraulic conductivity. We applied this approach at the German part of the River Inn, and as you can see on the figure here, we have a chain of run-of-river plants, and this is leading to more or less no free-flowing sections anymore. You can also see some characteristics of the River Inn here. And one common restoration measure here is the installation of bypass channels. And sometimes these bypass channels are constructed in a way that they can freely develop from a morphological point of view. And of course, you can also control the discharge, and this allows the artificial flushings. And so the basic idea is more or less on the one hand, of course, we have the longitudinal connectivity, but with the artificial flushing, the aim is to initiate bed load transport, regular bed alteration, remixing of sediments, or flushing out the fine sediments, so to say, to declog the river and restore the vertical connectivity. So I want to talk now about this bypass channel here. It has a length of 2.6 kilometers. The width is approximately 10 meters. There are no bank fixation. The bank for discharge is around 12 cubics. And we applied our multi-pack approach before and after a flushing event at these three different sites. You can see it on the pictures from our drone so that you just have an impression of the dimension of the bypass channel. And if you look now at the first results from the particle size analysis, this is more or less kind of a bulk sampling over a sediment depth of 50 centimeters. We have in the light color the situation after flushing. The darker color is before flushing. And the sieve curves here already show that we have a coarsening of the riverbed. Yes, and this is also confirmed if you look at the fine sediment contents here shown for sediments less than 0.5, 1, and 2 millimeters. They are decreasing due to the flushing, and the porosity is slightly increasing. So more or less we can say, okay, based on the particle size analysis, we get a coarsening of the riverbed due to the artificial flushing. Okay, Let's have now a look on the vertical profiles of the dissolved oxygen content and the hydraulic conductivity. So here we can also see an improvement of the values. Again, the colors or the light colors are after flushing, the dark colors before flushing, and especially in the upper 15 centimeters, yeah, we can see an increase for both parameters. And the interesting thing about this is actually that we can more or less determine the depth impact of the artificial flushing. Yeah, so what depth is mobilized during the artificial flushing. Good. Same river, different hydropower plant. So now we are in a residual river reach, and there we investigated 3 different travel bars. And again, we can see here the vertical profiles of oxygen and hydraulic conductivity. And if we look, for example, at the KB24 in the middle, we have the profile. I think it's not possible to see it. So it's an oxygen profile with the lowest values, which makes more or less sense if you look at the picture here. But most interestingly, we see that for the gravel bars, we get quite different profiles for the saturation, for the oxygen saturation. But the hydraulic conductivities also show some differences, but not in the same order of magnitude. And maybe one reason can be that we have higher respiration values at the gravel bar KB24. And this also underpins our assumption, more or less, that regarding riverbed clogging, we cannot work with a single parameter to describe this complex process. And that was more or less also one reason why we developed this multi-parametric approach towards an assessment of clogging. Good. Well, but how can we evaluate now those measuring results in terms of clogging or in terms of vertical connectivity? So what do we need if we want to do an evaluation? And therefore, we need reference values. Reference values that give us an idea what kind of physical values do we have in a natural state, or if we have in the rivers where we do not have any human influence. And therefore, we are currently working on a research project funded by the German Federal Environmental Foundation to develop a river-type specific evaluation concept. This means we are only looking at silicate-based coarse-grained rivers. And based on certain selection criteria, we selected 7 rivers. We did 3 measuring campaigns where we applied our multiplex approach. These were all sites where we also had data from the Water Framework Directive. And the table just shows the ecological status of the 7 rivers, as well as the indicator general degradation. This is an indicator describing structural deficits or, let's say, the morphology. The overall goal is to derive more or less some reference values based on the measuring results in these rivers. We are also looking at the catchment characteristic, and we also want to evaluate temporal aspects. But this is still ongoing, so this is still something what we have to do. We subdivided the rivers into 3 categories regarding the general degradation. So in total, we had 4 rivers where we have near natural state. We have 1 river with a poor situation and 2 rivers with intermediate situation. And just to show really some very, very preliminary results, if we look at the oxygen saturation, if we look at the fine sediment contents, we are able to find some ranges of values regarding the categories that we made for the general degradation. So we can see differences. We can also get some ideas about correlations, especially for the fine sediment contents and the oxygen. But as I mentioned, these are very, very preliminary results because we still have a lot of data that needs to be analyzed. And we also want to do further analysis with other biotic indicators. We are working together with the University of Koblenz in Landau, and they are doing, for example, some genetic analysis on myofauna. And this is maybe another biological indicator where we can find some correlations to our abiotic data from multipack. So to summarize my talk, I think we have seen that the multipack is an approach where we can measure physically based parameters to describe the phenomenon clocking. We have seen that we can measure vertical profiles for the dissolved oxygen content and the hydraulic conductivity. And this also allows us to identify, for example, certain locations of clogged layers. The particle size analysis and the porosity are results from a bulk sampling due to the free scoring. So this is a kind of an integrated results over a sediment depth of 40 to 50 centimeters. And of course, this is sometimes a bit challenging when we want to compare those data to the vertical profiles, yes. And regarding our current research, the main objective is really to obtain some reference values for unclogged rivers, but we also want to find functional relationships between catchment characteristics, water framework directive evaluations, and the new biological parameter based on myofauna. Last but not least, we also want to show on the temporal process of clogging, because it's not a static process. It's a process over time, and therefore we want to look at the hydrographs before our measuring campaigns to see if there are differences or not. So the overall goal, more or less, is that based on this unique data set, that we develop some kind of a multivariate evaluation concept for riverbed clogging or vertical connectivity. That's all, and thank you.